Hi everyone and welcome to my Go course. In this video we're going to talk about complex numbers data type in Go. So what are those complex numbers and why do we need them? First let's talk about real numbers. In our daily life we constantly use numbers. For example, to express the age we use positive integer numbers. To express the price we also use the positive, for example, floats. And to express the temperature, we use positive and negative floats and so on. All those numbers are real numbers. And in arithmetic, we represent those numbers by using, for example, the one-dimensional plane or simply axis. So this axis goes through all of the possible values of real numbers and it goes into positive direction through 0. And if we say there is some number, let's say 2, here here is this number on the plane or the axis for the positive real numbers, and let's say we would like to know the value of like 2 square root of 2. It's somewhere between 2 and 3 on this axis, and the value of pi is somewhere between 3 and 4 but closer to 3 on this axis. And here we also have negative numbers. And if we want to say we want to add, for example, we would like to perform an arithmetic operation like 1 plus 3, it just simply means that we take the number 1 and we just go 3 steps towards right from 1. So the result will be 4. And the same works with the subtraction. Let's say we would like to know the result of 2 minus 5. It means we take the value of 2 and just go 5 steps towards left because it's subtraction, and 1, 2, 3, 4, 5. The result will be minus 3. And what about the absolute value of the number? We know that the absolute value of a negative number, it's like the same number but without minus. So it simply means the absolute value of a number simply means the distance between from the number to 0. So for example, the absolute value of 2 is 2 because the distance from 2 is 2 to 0 is 2. And the absolute value of minus 5 is 5 because the distance from minus 5 to 0 is 5. So as simple as this. And here are some examples of the real numbers, like this positive integer number, this negative, and this floating, and so on. They can be also rational, like this one, or irrational, like this one, which has an endless, which has, sorry, endless sequence of 3 digits, and pi, another example of irrational number. And we go to the next step. Now we're coming to the next step, complex numbers. So complex numbers actually extend real numbers in math. So previously we talked about this real numbers axis. Now imagine we have one more axis which goes upwards. So the positive values for this imaginary, and we'll call this axis imaginary axis. So the positive values for this imaginary axis will go up from the 0 and the negative values will go down from the 0. And any complex number consists of two components, which is which is real, like any real number, like 2 or 3. For example, here we count from 0, we count 1, 2, 3. So the real part is 3, for example, and the imaginary part can be, like, for example, from 0 to 1, 2, can be 2. And this is how we represent them arithmetically. So the real part is 1, for example, 1, and the imaginary part is 5, is 5. And we can represent those numbers simply as vectors on the two-dimensional plane. And here are some examples of the complex numbers. By the way, I is actually the square root of -1. In arithmetics, the value of this operation cannot be calculated. That's why it's really good to use it in the complex math. So Um, this is about the complex numbers. And what is actually an absolute value for the complex number? Because for the real number, it's very easy. It's just the distance from the number to 0. So it's actually similar for the complex numbers. It's simply the distance from this number on the plane to 0. So it's simply the length of this vector. And if we know the real and imaginary part of this number, we can calculate this distance by using the Pythagoras theorem. So let's imagine we have a complex number a, which is 1 plus 5I. So the real component of this number is 1, and the imaginary component for this number is 5. So the distance to 0 will be the square root of uh, real power 2 plus imaginary power 2. And in this way, we'll know the absolute the distance of this vector. But is it really the absolute value for this complex number? Because let's imagine we have another number, complex number, like for example b, which is equal to 5 plus 1I. And the length from this number, the distance from this number to the 0 will be the same. So is it really um, convenient to represent the absolute value just simply as the distance? In case of the complex numbers, it's not. That's why we need something else. And in this case, we use phi, the angle between the real axis and the vector. And we can calculate this angle simply by using the arctangents, uh, the trigonometric function arctangents of this relation, imaginary part to real part. And we can also convert, if we have this kind of the absolute representation of the number, we can also convert it back to the arithmetic representation by using this kind of operation. So real part will be simply the multiplication of the r, the length of the vector, cos multiplied by cos of phi of this angle, and imaginary part will be just multiplication of the r and sinus sine of phi. And this is how we can just rewrite this representation, arithmetical representation of the complex numbers. So why do we need to use complex numbers? Complex numbers are used, for example, in electrical engineering when working with and calculating the alternating current, because alternating current is a sine function, and we just do not want to work with values at any given time. That's why we use complex numbers to represent, for example, the value, the maximum value of the current, and its phase as, for example, phi. And we can work with complex numbers in Go. Golang provides two data types for working with complex numbers, which are complex 64 and complex 128. And those numbers mean the precision, or the amount of bits for storing the values for these data types. Demonstrate the work with complex data types in Go by writing some code. So, as I said, Go has two data types for storing complex numbers. Let's create some variables of those data types, for example, complex 64. And complex 64 underneath uses two float 32 values. That's why its size is 64, so both 32. And there is also the second one, complex 128. So underneath it uses two float 64 values. And in the first case, it uses 32 values. So Golang has a built-in function to initialize um, these complex numbers. So it accepts, I'm sorry, it's called complex. It accepts two float 64 values. So the first one will be, for example, let's say 1, and the second one will be 3. And in this case, I've just created a complex number which represents this kind of number in math. And let's initialize this one using the same function, complex. and I would say it's -5 and 3.5. So in this way, I initialize this variable, and its value will be -5 plus 3.5i. So let's go and actually print those values. So I'm using the fmt package and the print line function, and I'm printing the first number, and I'll just copy paste this and print the second number. Let's run the code, and we see that Go treats these numbers really as complex numbers, and when we print those, we see this arithmetic notation of the complex number. Great. Actually, in this case, we use this complex function to create the complex number, but Go also provides the complex number of literals. So you can simply write 4 plus 6i, and Go will consider this as a complex number. So if I run this code once again, I'll see the value of C1 will be 4 plus 6i. Great. And the Go standard library also provides some function to extract the real and imaginary part of those numbers. Let's say, for example, I would like to print out the value of the real value of the real value of the sum of C1, um, just of C1, because they have different data types. And let's print it out. And the real value is 4. Yes, correct. And let's print the imaginary value of C2 by using this function, imag C2. And now we see its value is 3.5. So far, great. And we can actually, with those numbers, with those complex numbers, we can do any arithmetic operations like um, addition and subtraction, multiplication, division, because from the math point of view, those numbers are just vectors, and you can add vectors, you can subtract vectors, you can multiply them, and you can divide them, no problem. So here I'll just demonstrate this by printing out the C1 multiply 1 plus 5i. So I just use this complex number literal, and I'll just print ln, and I'll just clear this and run the code once again. And just at the end, we see the result of this multiplication. And previously, in one of the videos, we talked that in Go, the result of the square root of -1 is actually not a number. This is a special value of not a number. But Go actually has another package. I'm just going to delete all of this. Go has another package within the math package, and it's a complex package for working with complex numbers. So I'll import it. It belongs to the math package, and this package has its own square root function. And let's say I would like to calculate this value and print this out straight away. Print ln. fmt. I need to import it. fmt. Print ln. Yes. And I'll run this code again. And I see the value of this expression, the square root of -1, is actually a complex number. So Go provides this special package complex for working with complex numbers. And in this way, you can use this square root and you'll receive the actual complex number. And this complex package has actually many different functions, same as math package, but all of them are for working with uh, complex numbers. That's why it's really useful when you need to do some calculations with complex numbers. So this is pretty much it about complex numbers in Go. I hope you enjoyed the video. Uh, hit like button and write in the comments if you knew anything about complex numbers before watching this video. And I hope you liked it. Subscribe to my channel for the future updates. Thanks for watching and see you in the next one.